What you're seeing here is an AI playing a basic game where the objective is to jump over passing obstacles as they come by. But what's unique about this AI is that it learned how to play the game entirely on its own without having to give it any instructions as to what the rules are or how it should go about jumping those obstacles. So how does it work? Well, this AI makes use of two specific concepts that were inspired by the way natural biology works: artificial neural networks and genetic algorithms. An artificial neural network is a machine learning model that attempts to mimic the way your brain works by replicating the functions of neurons in a mathematical way. The neural network I created for this example is a simple 3-layer feed-forward neural network known as a multi-layer perceptron. This consists of an input layer, a hidden layer, and an output layer. The input layer can be thought of as the eyes of the neural network. It reads in the x and y values of our current obstacle along with the y value of our player. The output layer gives us a probabilistic value between 0 and 1. If the output is greater than 0.5, that means our network is telling us to jump. If it's lower, we do nothing. Now, the neurons of each layer in the network are interconnected by a series of weights, otherwise known as synapses. Each weight has a specific value assigned to them, and these are going to be set to random when we start. And the data flows to the network by multiplying each of the current neurons by their respective weight value, starting from the input, then taking the summation of them, applying a nonlinear activation function to get the value of the neuron in the next subsequent layer. This is repeated throughout the entire network for each layer until we get our output. So what's an activation function and what is its purpose? Well, conceptually, an activation function allows us to simulate the action potential of neurons in your brain to determine whether a specific neuron will fire a signal to the next neuron or not. It also introduces nonlinearity into the model and makes it differentiable. So if you're trying to approximate the function of some set of data, you usually want your decision boundary to be nonlinear. You want there to be curvature in your model and you want your data to fit the model as best as possible. If you don't have an activation or transfer function, your output will always end up being linear, and for most cases this isn't really a good approach when trying to model complex data. In this example, I'm going to be using the logistic sigmoid function, which is f of x equals 1 over 1 plus e to the negative x. This allows us to squash our values between 0 and 1. Now, there's some other popular activation functions out there, such as the hyperbolic tangent function, rectified linear unit, and so on. There's a lot of them. The sigmoid is usually the most common activation function used in neural networks, so I decided to go with that one. Now, in supervised learning approaches, neural networks need to be trained with an existing set of data to predict an accurate output. And this is usually done through a process called gradient descent, where we compute the error of each output in the training set and use that to find the partial derivative with respect to the weights in our network's layers and update each one in the direction where the error is minimized, propagating one layer backward at a time. Now, this approach is really only good if you have an existing data set to be able to train your network with. I could record myself playing the game and then use that as training data, but we want the network to learn how to play the game by itself. So how would we be able to optimize the weight values without one? We're going to use a genetic algorithm. So a genetic algorithm is an optimization technique used to maximize the specified fitness function through a process similar to biological evolution. In my example, the fitness function is simply the distance the player travels through the game, and we want to be able to make this value as high as possible. So we start each game with 10 neural networks initialized with random weights. We'll call this our initial population, or generation 1. We then let the networks play the game, and once they all lose, we take the top 2 networks with the highest fitness and we breed them together to create offspring for our next generation, discarding the networks that did poorly. You can think of this process sort of as natural selection. So how do we breed our networks together? Well, you can think of the process like chromosomal crossover, where each child has a combination of the parent's DNA, or in this example, the weight values. Some genetic algorithms use a technique called single-point crossover, which selects a random point between the parent's values, and a child is created by combining the two where they split. This didn't work out too well for my model, so I decided to use a technique called uniform crossover, where each weight of the child has a 50% probability of being either parent 1 or parent 2's weight. I also applied a 5% mutation rate to each weight, where a random value is then assigned instead. This allows us to explore the fitness landscape so we aren't confined to using variations of our initial weight values. Without mutations, there's a good chance our networks might never end up finding a solution, and it's a key component when designing genetic algorithms. In the first few generations, the neural networks really have no idea how to play the game or how to go about jumping the obstacles. My cat could probably play the game better at this point if I had to be honest. But after a few generations later, we start to see the networks beginning to get better and better at playing the game, until eventually we find a network that can play the game indefinitely without losing. So that wraps up everything for this video. I hope you guys enjoyed, and thank you so much for watching. If you're interested in downloading the project and looking at the code for yourself, I have the Maven project uploaded to my GitHub page for anyone to access.